All right, today's lesson is on a topic called similar solids, and we've talked about similarity in this class from triangles to quadrilaterals to circles, and now we're in three-dimensional shapes. And the concept that is the same for all similarity is that solids have to be the same shape and their sides are going to be proportional. Their dimensions are proportional. So it's the same shape. So if it's a cone, it better be a cone. And their dimensions will be proportional because not all cones are actually proportional. One topic that will come up quite a bit in lesson today is this idea of similarity ratio. And this is going to be the ratio of the corresponding linear dimensions of two solids. So a linear dimension would be a radius or a height or that type of dimension. All right, so if we look at this here, this example here, we're going to go through how to identify if solids are similar based on linear dimensions. There's two ways we're going to identify similarity. One is by linear dimensions and one will be by volume, which we'll talk about in a few minutes. So are these two things similar? So if they are, they'll have the same similarity ratio. That would be true. So what we want to do is match up parts. So the radius in the left side, the radius in the left is 3, and the radius in the right is 9. So that would have a ratio of 3 to 9. The height on the left is 8. The height on the right is 26. When you divide 8 by 26, it does not equal to the same ratio as 3/9. And so these two shapes are not proportional. So again, a summary of this, we want to compare the radius to the radius and the height of one to the height of other and make sure the comparisons are the same. So in this example, I went left divided by right, left divided by right. You could also do right divided by left if you wanted. So just make sure the ratio is set up appropriately with the value coming from the correct shape. All right, here's another two of what is a square prism here. So we have a square-based prism. So what we want to do is match up parts. So I'm going to match this up to this and this up to that. So you see how these are matching. Now, technically it doesn't matter because they're both the same, but we'll talk about in a second, the most common mistake is not matching things up appropriately. What sometimes problems will be shown as is a 3D solid tipped sideways. And because you're gonna have to match up the longest with the longest and the shortest and the shortest and the middle with the middle. So keep that in mind. All right, so again, what I was just saying is match up the parts. The most common mistake is not matching up the longest side to the longest side, the shortest to the shortest, and so on. So make sure you're paying attention to that. All right, so if we were to go through, the left side divided by the right side, the left side divided by the right side, we get a value of 4/3 for their ratio. Because these are all the same, they are proportional. So that's what we're looking for. Every single ratio has to be the same for each dimension of the shape. If two are the same but one is different, it's not proportional. They all have to be the same to be proportional. All right, so there was an example, two examples of how to find out if something's similar based on linear dimensions. Now we're going to talk about what happens if we know their volumes. So in this particular case, we're going to compare ratios of side lengths. So we get a side length of 1/2. So the smallest to the smallest, the middle to the middle, and the largest to the largest. So smallest, middle, and large. So we have 1/2, 2/4, and 3/6. And all of that would simplify down to 1/2. So our ratio of side lengths is 1 to 2. If we do the volumes, the volume of the left side is going to be a volume of 6, and the volume of the right side will be a volume of 48. Now, a lot of people will be confused and say, well, if they're a ratio of 1 to 2, shouldn't the volumes be 1 to 2? But that's not actually what happens. In fact, if we do 6 divided by 8, we get a ratio of 1/8. And what that comes from is we are going to cube the similarity ratio. So if we go back up to the linear dimension, the similarity ratio is 1/2. So if we cube 1 and we cube 2, we get a combined fraction of 1/8. So this is where it gets a little confusing because we have to cube the dimensions when we are using volumes. To compare volumes, we have to cube dimensions. All right, so in the notes here, the idea is whatever the dimension is for A and B, to find their corresponding volumes, we do the cube of their ratio. So we cube whatever A is and we cube whatever B is. That would be the ratio of the similarity of the volumes. Now what they want you to do is find the ratio of height to these two volumes. So what we're going to do is we're going to cube root both of these things. So if we cube root this and cube root that, so we cube root 1000 and cube root 2197, we get 10 over 13, right? So one way to do it in the calculator is our cube root button, and then use ND. And in ND, use 1000 over 2197, and you would get a simplified answer of 10 over 13 in the calculator. Okay, what happens if in example 4 we have pi written down for volume? Because in the volume in example 3 there was no pi. We've talked about this many times. Pi is just another number, and we can't get rid of it. We have to include it in our problem. So in this case, what we're going to do is take the cube root, right, and then use the ND key, so cube root and then ND, and then type this in. It's difficult for me to type this on the computer. So on the top will be 20 pi, on the bottom will be 160 pi. And if you hit enter, you should get a similarity ratio of 1/2. So their linear dimension ratios will be a similarity ratio of 1/2. All right, here's the next one. So we have 250 and 1458. So if we did what we did before, what do? We need to figure out the similarity ratio by taking the cube root of each of these. And you should get a value of 5/9. All right, down here, this is a little bit trickier problem. So what we're doing is we're taking a linear ratio based on volume to a different measurement. So they tell us that the rectangular prism is 6 inches high and holds this amount, 3.25 pounds. How much detergent would a similar box that is 8 inches high? So what they're doing is they're changing the heights. So if we cube the ratio in this case would be 3 to 4. We can write it as 6 to 8, which is fine. And so then what we do to find x, the value of how much would the 8-inch high box hold, we make a proportion. Then we cross multiply. So this x times 6 cubed, we cross multiply and get 6 cubed times x. Then we have 3.25 times 8 cubed. And when we multiply and then divide by 6 cubed, you would get a total value of 7.7, which realistically makes a little bit of sense here, where we're going to get a value bigger than 3.25, but not too large. So if the side is 6 and this side is 8, you know, it's going to have a little bit more volume in there. In fact, it's a little bit more than double, but you're not going to get an astronomically large number. All right, here's another one here. So a pyramid weighs 0.55 pounds, so it's a very tiny one. How much does a similar shaped pyramid weigh if its dimensions are 4 times as large? Well, if the ratio is going to be 1 to 4, the original to the new is 1 to 4. So the volume ratio will be 1 cubed over 4 cubed. So the volume ratio will be 1 over 64. So we have our volume ratio set up on the right side on the screen here. So 1 over 64. And then the weight ratio. So the original is a ratio of 1, and that has a weight of 50.55 pounds. And the one we want is going to go on the bottom. So we cross multiply and then divide, and you should get 35.2.